One more minute. So you can see both the diagrams, right? Yes. Everything visible? Yes. Anyone? Font size are okay?
Yes, sir.
Okay. Okay, so let's start. So let's just recall what we were trying to do. Okay. So we had a bottom plate. In fact, we have bottom plate. And above that, we have some liquid, Newtonian liquid for the time being, whose height is h. Okay. Whether it is large or small, that we will see. When we will say it is large, when we will say it is small, because something is large or small, that is always a relative term. Okay. So we start pulling this plate, bottom plate, flat plate, with a fixed velocity u for all t greater than equal to 0. And what we have seen in the last class, or what we discussed, that gradually the effect of this stress or energy which we are providing here, that will propagate in the liquid in y direction. And this is the x direction. So liquid is moving in x direction. Okay. So that's why the only velocity component which exists is vx. And if you remember, we also discussed, since there is a friction between these fluid layers as well as near the wall, okay, which we know as viscous effect or viscous drag, there will be a velocity profile. So this layer will always keep on moving with velocity u, and then if it will go up, the velocity will decrease. Okay. So there always will be a velocity profile. That is point number one. So the only velocity gradient which we discussed, which survives in this problem, 2D problem, is dou vx by dou y. And then we also said that there exists a length scale delta, which is time dependent. I am saying this is the length scale up to which the fluid layer will get disturbed and will start moving. So what will be the value of this delta at t very close to 0? So my question to you is that if t tends to 0, delta tends to what? Anyone make a guess?
0.
0.
0. Very good. 0. Because the disturbance has moved up to very small distance. And as t will grow, the delta will grow. Okay, wonderful. So basically, fluid layer situated, let's say, at this location and at this location, there are 4 locations. So whatever this fluid layer is experiencing right now, the same thing will be experienced by this layer at later times, and then this layer at more larger times, and so on. In other words, this fluid will experience the similar disturbance earlier as compared to layer at 2 and 3 and 4 and so on. Okay. So with all the layers, now I'm writing very important term. With all, if you consider the various layers, the phenomena or the disturbance or the stress, the stress propagation at different layers, the phenomena for all the layers, it's similar to each other. This is called self-similar. So if this layer is, let's say, attaining u by 2 at some time, then layer above it will attain the same u by 2 at some later time. So basically, if you consider each layer, whatever is happened with that layer, the same thing is going to occur with layer above it at later times. Such kind of phenomena is called self-similar phenomena. Okay, just give me a moment. It's an important call. Sorry for the interruption. Yes. So what we are doing, just a moment. First, let me switch off my phone. Otherwise, calls will keep on coming. Right. Yeah. So what we are saying that this phenomena is self-similar. So that is point number one. Now, if you see the velocity profile, let's say, without solving this question, if you want to, let's say, know the velocity profile, okay, then how it will look like. So if you are not clear with the plot, let me explain you this plot. So on the x-axis, we have this Vx, velocity in x direction, whose maximum value is u. And this is the height, this height, the y direction. Okay. So if you will consider, let's say, very close to this wall at lower y, okay. So what will happen that at earlier times, only this lower layer will move. So only the lower y will have some, significant value of velocity, right? And this will always, and this y equal to 0, this is y equal to 0, this is always velocity u, you see. Y equal to 0 will always remain at velocity u. Otherwise, so only up to some, let's say, some time has passed. So up to some y, you will see some positive value of velocity. But after that, particular, let's say this is delta. So beyond delta, on y-axis, everything is 0. So this plot, let's say at some earlier time, this is like this. So up to this delta, if you see different y coordinates, you have some velocity, some positive value. Beyond this delta, velocity is 0. Again, after some time, if you see the velocity profile, now it will look like this. What happened? Now delta has increased. So probably delta is now this much. So up to this value, you will have some positive value of u for these different y coordinates. And beyond that delta, velocity is 0. So this way, this velocity profile will evolve. So whenever it will be asked to you that draw the velocity profile in space and time domain, or draw the stress profile in stress and time domain. That's how you should draw. Okay. So either you can take this x-axis or this x-axis. It depends on you. This is convenient for me because this is my plate. So this I have kept as velocity axis. This is my height. So this I have kept as y-axis. Okay. So this Vx versus y at different times. So probably this is time t1, time t2, time t3, time t4, and it is increasing in this manner. So t4 is greater than t3, is greater than t2, is greater than t1, and so on. Okay, right. So if you understood this much, if there is any doubt, let me know. Meanwhile, I will wipe it. So all you should remember here is one word itself similar. Self-similar phenomena wise also and profile wise also. You see that these all velocity profiles at different time are not identical. They are similar to each other. There is a difference in saying they are identical and they are similar to each other. Okay, so they are self-similar. Right. Okay, what else?
Sir, what is
So,
exactly the delta of T?
sorry, come again. Let me increase the
What is
voice.
exactly delta?
Just a moment. Yeah, what you were saying?
What is delta exactly?
What is delta in this?
Exactly what it represents,
We will
delta.
come to that. We are coming to that. We will start now. That is the starting point. That what delta represents. Very good. Because this delta is the like we will confront this delta throughout when we'll solve this problem. Good. If you remember last class, we were trying to get the order of magnitude of the various terms in the governing equation, and we are discussing with Anik. So what he said. So our governing equation, if you remember, is dou vx by dou t is mu by rho dou square vx by dou y square. That was our governing equation. And from now onwards, mu by rho we will replace by a new term. Where is the y? So mu is the viscosity and rho is the density. So this will be replaced by new term mu. So let me write somewhere mu. Our mu will be mu by rho. This mu is called kinematic viscosity. Kinematic viscosity. But I'll tell you something more meaningful rather than this name. You have done mass transfer. Can you tell name the equation, like write the equation how it looks like? So if you remember, dou c by dou t is equal to d dou square c by, let's say, dou x square, dou y square, whatever it is. What is this d?
Diffusivity.
Diffusion
Diffusivity.
coefficient.
As we say diffusivity, it's molecular diffusivity, right? These both equations are identical in the sense that physical quantities which we are dealing with different, but I mean, all the only thing is that there are different variables and different constants. So, taking the analogy from this mass transfer equation, this is very well known as. I'll remove this, and you can make a guess what we should call it. New, if someone knows already.
Momentum diffusivity.
Momentum diffusivity, right? So that is the analogy. Okay? That is the region we call it momentum diffusivity. And see, it is very logical also. You will realize that it will depend on both viscosity and the density. Okay. Imagine that your liquid is not so viscous. If liquid, in fact, when you are pulling it, there is just see generally what we say here we have a no slip condition at the wall. What does it mean by no slip? No slip means the molecules of the wall gets attached with this fluid layer very close to this, and it try to drag with it, so that whatever the plate velocity has, the same velocity will have the layer situated at very close to y equal to 0. That is called no slip condition. Means there is no slip between the solid, this flat plate, and the fluid layer adjacent to it. That is called no slip. No slip doesn't mean velocity 0. Don't get confused. No slip means the flat plate or the solid surface and the fluid layer adhere to it. Between them, there is no relative slip. So both will move with the same velocity. So if this plate is stationary, the fluid layer will be stationary. If this plate is moving with some velocity, the layer adjacent to it will have to move with the same velocity if we say there is a no slip condition. But many times it happens that if your liquid is not viscous enough, this will start moving faster, there will be a slip. Once there is a slip, then probably you won't be able to propagate the moment up to larger heights because it is not disturbing the other upper layers. So that's why it depends on mu also, and as well as density also. Okay, so that is the small discussion on momentum diffusivity. So now we understood this one-dimensional momentum transfer in time domain. We are interested in time evolution, right? So just note it, this term momentum diffusivity. These terms are there in your slides. Okay. And anyway, lecture is getting recorded, so you can make your notes. Now, so let's come back to our non-dimensionalization. So as Anik said, the characteristic, so this is the u velocity. As Anik said, the characteristic velocity scale or the order of magnitude of velocity is u. And now we are thinking what is the characteristic of value of y, typical value of y or a scale or order of magnitude, and what is the typical scale for t. And then we are thinking what we should do. One suggestion, Anik said it should be h. And then someone suggested no, it should not be h, it should be delta. So which one is right, which one is wrong? Both are correct in two different time regimes. We will see. For earlier times, now when I say earlier times, what does it mean? Because something is earlier, something is later, again it is relative. 5 seconds can be a very large time with respect to 5 femtosecond, 5 nanosecond. Okay, so that is also very important. So there are two guesses for y, h and delta. Okay, let's say right now I say okay fine, characteristic length of y is h. We consider what Anik suggested us, let's say h. Then see what is the time scale for t, typical time scale, because we don't know yet what is the characteristic or typical value of time. Okay, since you know the time scales for other two variables, the characteristic values or order of magnitude or rough estimate of other two physical quantities, we should be able to get the order of magnitude of t, provided you are saying both terms are important for you. Since both terms are important for you, on both sides, the order of magnitude of terms should be same. And that is called order of magnitude analysis. See, it's like this. A plus B. A is order of magnitude of A. So let's say you are going from Kharagpur to your home located at Kolkata or located someplace, let's say New Delhi. So A is the distance from Kharagpur junction to New Delhi junction or airport, whatever you want to say. Oh, there is no airport in Kharagpur. So, and B is the distance, let's say from here to station and from New Delhi station to your home. Okay. So can we say the order of magnitude of A is very, very greater than order of magnitude of B? Isn't it? Let's say A is 1000 kilometer, B will be around 10 kilometers. You agree? Adrija? So in that case, what will happen? Both term will survive or we can drop one term?
So we can drop B.
Yeah, so B can be dropped because order of magnitude of B is significantly less as compared to order of magnitude of A. So similarly, if you will drop any term here, then story is finished. Then there is no big deal. Okay. So we are saying both terms are important. Then only we will get the relevant information which we are looking for, velocity profile as a function of time, Vx of y as a function of t. So since both terms are important, let's do this order of magnitude analysis. So probably now, from now onwards, you will understand the significance of this term and you can use it in other streams of, whatever profession. This order of magnitude analysis, you can do anywhere. It's a quick calculation. Order of, what is the order of magnitude? That's what you want to do, order of magnitude analysis. Good. So, dou Vx. Now, many people will get confused if you want to know the order of magnitude of dou Vx, it will be u minus u0. No, this is the difference of velocities. You all have done numerical method. When you will try to solve this problem, if you will take the difference, this is the difference of velocity at two different times. So let's say at some time velocity is, if the value of u is 5, at some location, at some point of time, some layer has taken velocity 2, and after some time that will take velocity of 2.2, 2.3, something like this. So the difference will have the same order which this u has. Okay, so never think that if Vx has characteristic value u, dou Vx will have characteristic value u minus u0. No. If you different two quantities of same order, you expect that you will get the difference of the same order. Because if the difference will go to 0, this problem will not be valid. If this difference will go to 0, then there is no point of solving this. Okay. So the typical, so the characteristic value of the numerator will be u. This we are interested in. What is the typical value of t? We are saying this capital T, let's say. Okay. Or you may get, okay, T is time, not temperature. Okay. This must be roughly equal to, you cannot put exact equal sign, equal to nu what is the characteristic value of this others? What do you think?
U by x square.
Yeah, very good. So this is the difference, taking difference two times. So this is simply u, very good. And y, this is squared quantity by L. What's that, L square or what square? Others, what you said?
X square.
X square, yeah. So since we are considering a next statement, let's say is right, so this. So you get cancelled, and the characteristic value of time which we are getting is, you can see here. Yeah, yeah. Yeah. So if you see here, t, the order of magnitude of t is h square by nu. Okay. So by knowing the order of magnitude or characteristic value of other two parameters, physical quantities, we now know that if your time is of the order of h square by nu, then both term will survive. Okay, and you can take this h as characteristic value. So when we can take h as characteristic value, if I am analyzing the problem in the time, okay, which has value typically in the range of around this h square by mu. If the time, so let's say you know the h, let's say 5 meter, 1 meter, whatever it is, and you know mu is nothing but mu by rho. You know the, if I give you water or ethanol or honey, anything, you will know the viscosity and the density. And let's say you have calculated t, and t is coming out to be, let's say, 60 minutes. So this, you can take this h as characteristic value. Let's say if you are solving your problem, t greater than 40 minutes and less than 80 minutes. So between 40 to 80, it will be a good choice. H will be a good choice of characteristic length scale, or order of magnitude of this y will can be h. Clear up to this point? If you have anything in coming into your mind, you can ask, or wait for a few 4 minutes and then you can cross question. Okay. So this is important here. I have to wipe it because the scarcity of space, but it is there in the recorded lectures. You can go through it again. Okay, so what we said? We said this. We said if our time scale, or the time in which you want to know the information, if that time is around this value, your characteristic can be h. What if my t is very, very less than x square by? So my time scale is very, very small as compared to this time scale, or t. This is nothing but if t is very, very less than capital T. In that case, what can be the characteristic length scale? Any guess? Others? Or Aditya, you want to make a guess? You can try. नहीं है कोई और? Muskan, you want to make a guess? What can be, if you want to analyze the problem, let's say within 1 or 2 minutes, let's say typical value of capital T is 60 minutes, but you want to know the information within 10 minutes. What you would like to take the characteristic value of y? Any guess, Muskan? Rakshit, any guess?
Sir, delta.
Delta. Very good. Because then it is very early times. So this disturbance is very far from the top layer of the fluid. So Rakshit, if you take delta, very good, as characteristic length, which is function of time, then what will be the characteristic value of time? Make a guess.
Delta square t by nu.
Rather than, see, delta is good, but the problem is delta is growing with time. So this typical value of t is nothing but the real time, isn't it?
Yes, sir.
Because see, you are saying delta will go with the real time. So then the time, characteristic time scale will be the time scale at that time itself, because delta itself is a function of time.
Yes.
Okay, right. Now, if you understood this discussion, this t is very, very less than h square by nu will be called early times. And for this early time, h can be treated as, anyone make a guess? For early times, h can be treated as very large. That's all. So infinity is nothing like real infinity. It is always relative. So Akshay, is it clear when h, you will say h is very large, or what you call infinity? Akshay? Akshay Agrawal? कोई अक्षय का दोस्त है, उसको मैसेज करो, उसको मैं क्लास में खोज रहा हूँ। एनीवे, सो गौरव,
Yes, sir.
yeah, so is it clear? H, what does it mean by h tends to infinity?
Yes, sir.
What does it mean?
So it means it has large values.
So when we can say h is very large? Yeah, you are right. H tends to infinity, h is very large. Mathematically, h tends to infinity. When we can treat h as a infinite, a very large quantity? When t is very, very less than this
H
one.
square over mu.
Right. Okay. So that thing should be clear that h is not always infinity. At some point of time, when your time scale will be order of this capital T, h will be treated as a finite quantity. But for very early times, let's say if capital T is 60 minutes, for initial 4, 5, 6, 7 minutes, let's say h can be safely treated as a very large quantity, and we'll take the mathematical advantage of this. So, Anik, clear? This whole discussion.
Yes, sir. Yes, sir.
Yeah. And now someone is asking what is delta. Someone has asked in the beginning. Is the meaning of delta clear? It will again come in the problem, but up to this discussion, that when we take delta and when we take h, h is fixed, and that we can take as characteristic if capital T is of the order of this time scale. Otherwise, you take delta, but delta itself is a function of time. It is growing. So at a given time, that time itself is its characteristic value. Right? Okay. Another learning. So this another very important learning is Rakshit was saying that T. So what we say as if you see this equation, del square dou Vx by dou T is equal to dou square Vx by dou y square. So probably from next week I'll get again the excess of that studio where I take the class, but today we have to manage with this. Anyway, so this is u by time scale, the real time. We are doing the order of magnitude analysis for this regime, this time regime, early times. This is roughly equal to u by this time delta square. So delta and mu here. We have here mu. Okay. So see what is delta is coming out to. Delta is roughly equal to root nu t. What information you get here? See it carefully. It means if you know the time, you can make a guess. Not guess. In fact, you can make an estimate that up to what time this disturbance has penetrated. So at t tends to very close to 0, delta is 0, and then as t will increase, since you know the value of nu, up to that height, roughly, its order of magnitude, the delta has reached or the disturbance has reached. And that's why this delta, anyone make a guess what we can call it? It's called momentum diffusion length scale. Okay, so this delta is called momentum diffusion length scale. Now, if anything is coming in your mind, you can share with me. Let's take 1 minute pause if you want to ask something. Anything? So, Tanmay, more or less it is clear. Of course, when we'll move more and more insight you will get. But otherwise,
Yes, sir.
okay, if anything seems bit I mean, abstracted or lost, feel free to interrupt me. Good. So Akshay Agrawal is here, by the way. Any of his friends, just inform him. I want him in the class because he's in the class, but he's not responding. Otherwise, I'll write to him if he doesn't come to the class today. Okay, thank you. Then we move ahead. And now, what else? Right. Now, I have a very interesting question for you. Let's say Nitin can answer, or anyone can answer if you just make a guess. If I'll ask you, we have so many curves. Can we do something here in this curve? I mean, with x and y axis, so that we can get only one plot. Because the whole, the whole effort is to unify things in any branch of science or engineering to get a master equation rather than so many curves, so many equations. So can you make a suggestion what you'd like to do with x and y axis so that we can get a one plot? A guess. What will be your guess? Let me draw again x and y axis, and then you make a guess. So what you would like to do with this so that we will get a one curve? So, any idea?
Sir, like,
Any suggestion? At least let's say if I'll ask you what we can do with this. Any idea? I'll give you a hint. Whatever will happen, let's say at layer 1, the same thing is going to happen sometime at layer 2. So what we should do with Vx?
so like, do we have?
Sorry?
Yeah, so I was asking, like, do we have to merge these two
Like you have to
plots?
play. Okay. So what you can do, you can divide something with this, add, subtract, like mainly division or multiplication. That is preferred with this axis. So any number
Sir,
with which we can divide this axis.
yes, sir. We can divide Vx by u and y by
Very good.
h.
Vx by u. Yeah, and this one for
Y
early
by
times.
h.
No, early times. So you are on the right path, but early times, not time of the order of h square value. Early times.
Then sir, delta.
Delta. But delta itself is a function of time. And what value of delta we got for early times? Order ut,
Root of.
right?
Yes, sir.
From the order. So basically, if you have, let's say data wise, if you have, let me draw it here. This is value of, let's say, T1, T2, T3. Okay. Or not like this. First, make the chart for T1. Let's say this is at T1. This is my Y, and this is my Vx. Okay. And at some time T2, this is my Y, this is my Vx. Some data points. And so on at T3 and so on. what you should do, make a new column, a new y. Let's say it y non-dimensionalized. You can say this. Okay. And this is Vx non-dimensionalized. So what you do, you say create a new column, say y bar, and y bar is going to be all the data points divided by 4 new t, where the value of t here is t1. So this is nothing but y bar is nothing but in this column you have y by root new t1. And in this column, here create a new column, Vx is non-dimensionalized velocity, and here it is nothing but Vx by u. So your new revised x and y axis or data points is this one and this one for time t1. Do the same for t2. For t2, y axis, the revised y axis, y bar will be y root new t2, and Vx will be Vx by u. Keep on doing with all the curves, and then draw it. This new y, new velocity. New y means non-dimensionalized y, non-dimensionalized velocity for different time. And this we are going to do in one of the assignment. And indeed, you will see all the curves are on top of each other. These all curves will collapse into a single master curve. Okay, we will see it. And that's why we said it's self-similar, because with some treatment, this all curve will be on the top of each other, because they are not identical, because you are not just subtracting the x or y axis. You are multiplying and dividing with some complex mathematical variable. For example, this root nu t. Okay, and we'll get a single master curve, and that we will see. You are going to do it in future classes or in future assignment. And if that is the okay, is this treatment clear? So
Yeah. Yes, sir. Clear.
yeah. Tejas, did you get this? What I'm trying to say here?
Yes, sir.
Tejas.
Yes, I got it.
Okay, perfect. And we will see. Since you will do, you will get more feel. Okay, right. So then, what is the message here? The message is as follows. As I say, our main goal is if we can get a unique equation or a master equation or a unified, something unified, more unified. And what we are making a strong statement here by making a guess, and eventually we'll see it. Yes, it is true that we can say Vx by u is function of delta, which is y by u. Not delta. This is delta. Y by root nu t, and this is variable is typically named as similarity variable, because curves are set similar. Similarity variable. So basically what we are saying, the non-dimensionalized velocity, what we want to say it, let's say Vx bar is function of eta. Eta is this y by, so eta is nothing but y by root nu t. So what I am trying to do, the problem which is a PD, which is in domain and time and space domain, I am trying to create only two variables. So Vx is function of y and t. What I am trying to do is I want only one independent variable and one dependent variable. So my Vx bar is function of this eta. And eta is a similarity variable which is function of both space and time. That is the beauty of this approach. You are combining space and time so that you can reduce the two dependent variable in one, two independent variable in one independent variable. Because here you have done nothing. If Vx, you just dividing the constant value, so it's still, there is no big deal with it. The big deal is here. You are combining y, the space and time, to create one single variable, eta. Okay, and this is called similarity variable, because we will see these curves are self-similar, because after this treatment we'll get a master curve, and master curve equation will be this. We will see what will be the functional form, that is still to be revealed. We will see that. Okay, Now let's come back quickly to our assignment because this is connected to this. So let me write this. So the assignment which I have given you, it will carry significant marks, let's say 2 or 3 marks at least from my part. Okay. So my portion is 25. Professor SDG is probably 75 or 30, 70. That we have not decided yet. But the assignment which I have given is very important. Even if somebody copies, I don't mind because there is a lot to learn. And those who are copying it without learning, believe me, we won't be able to do anything in the exam. So try to do it by round. Now let's discuss on those fronts, like how you are going to do this assignment. So what we have seen is this is our equation. Okay. And this plate is moving with constant velocity. What I have asked you in the assignment is rather than constant velocity, you are maintaining you are pulling this plate with a constant stress, shear stress, tangential. Okay. Otherwise, everything is same. So first of all, you have to convert this equation into. I have asked about the stress profile, not the velocity profile. Okay, because from stress profile you can derive velocity profile. Why? Because stress is connected to velocity with this relation. Mu, you all know, since it's a Newtonian fluid, tau xy is nothing but mu dou vx by dou y. This is the shear stress here, tangential stress. Okay. So in assignment problem, you have to convert this equation into stress. So what you do, you write it in this fashion. Dou of dou x, dou vx by dou y. Okay. And then what you do is as follows. Sorry, this is t. So this mu you can take inside. Okay. And then what we are going to do is as follows. Oh, there is rho here also. No? So this is nu, not mu, not mu. This mu is here. Okay. Now what you do, you take derivative with respect to y both sides. Right. And here you can use the exchange of variables. If you use the exchange of variables, it will be dou of dou t, dou of dou y, vx. Here we have dou of dou y, and this is nothing but mu by rho. Again, dou of dou, mu by rho, dou vx by dou y. Okay. Now what you do?
So what is dou by dou like?
Sorry,
Should be dou
come
by
again.
dou some. Sir, like
Oh, sorry. Yeah. So this should be. See, this is a double derivative, isn't it? You see the equation? Dou vx by dou t is dou square vx by dou y square, right? So dou vx by dou y, you can write how you write it. Like, okay, right. Bit more properly so that you will not get confused. Let me write it. Go step by step first. So dou vx by dou t, keep it as it is. And here we have mu by rho. mu by rho. So dou Vx by dou t, mu by rho, whoever I asked, we will write it dou Vx by dou y by dou y. I think now it makes sense that why I missed it. Clear? This double derivative is nothing
Yes,
but
sir.
this.
Yes, sir.
Okay. Now you take this time differentiate both sides again with respect to y. So again we are differentiating with respect to y, that we dou by dou y, dou by dou y, and there is a mu by rho here. Okay, right. And now I'm going to use exchange of variables. So exchange of variables means I can write this way, dou of dou t, so that you can see in mathematics that what is the exchange of variable rule. So this will come inside, and this we are not going to do anything as it is, dou of dou y mu by rho dou vx by dou y of y. Okay, and then what we are going to do, multiply both sides by mu, because we need mu here also and mu here also. Okay, now tell me what is this quantity. Let me circle it for you. This quantity is what? Yeah, what is this quantity? Achal, what is this quantity? Mu dou vx by dou y.
Let me just a minute.
Yeah, take your time. Mu dou vx by dou y. What is this quantity? So what is this quantity, anyone?
So stress.
Yeah. So dou by dou t tau xy, very good, is equal to dou by dou y, mu by rho, you can write mu because this is as it is. And what again, this is also tau. So dou of tau xy, because that is a xy. And then again, this is nothing but double derivative. Okay, first see it carefully here, what I have done. I have purposefully created these two terms both sides, so that I get stress. Now there is no velocity. Okay, and once this is done, now your equation is in terms of stress. And the same problem has been solved in the slides which I have shared with you. So the half of the problem is already done. You just need to understand it and copy it in your assignment. So the equation which we'll get in terms of stress is dou of tau xy by dou t, and then you can take out. So dou square tau xy by t. So you get again everything identical, except rather than velocity, now we have stress as a function of time which you want to know. So so that is one part of assignment. Then you have to write the boundary condition, initial condition. Okay, and this boundary and initial condition are going to be different than this problem, because here you are pulling it with same velocity, so that we will solve in the next class. But here you are pulling it with constant stress, both are not same. Okay, so this you are going to solve using Crank-Nicolson, for which you need initial and boundary condition. So let me write it quickly. Initial condition means what is happening at t equal to 0 for all y. So since initially everything is stationary, nothing is moving, the shear stress is also 0 everywhere. This is initial condition, because you want to solve this equation. And then boundary condition. Boundary condition is going to be at y equal to 0, tau xy is equal to some tau naught for all t. And what is at y goes to, so I am analyzing this problem for t very, very less than x square value. Okay, so at y equal to, rather than h, what I can write here mathematically? Anyone? What is this h? Infinity, because I am analyzing the problem for these early times. So at y tends to infinity, what will be tau xy? I have two boundaries. Okay, this is called semi-infinite. What it will be? Stress. So if you are analyzing the problem early times,
0. So
0,
0.
because disturbance has not reached to that value. Exactly, 0. That's it for all. So with this, you try. So now what you need to do, you need to solve this numerically. I will put a video over this, a very small, brief idea of steps how you are going to do, not the Crank-Nicholson method. Just I'll again repeat these things and I'll tell you how this problem and this problem are slightly different. When we are pulling it with constant velocity, that we will solve in the class, and when you are pulling with constant stress, that you will solve. So you won't be able to submit it on Monday. Don't worry about it. I'll give you some more time. Okay, maybe next Monday, not the next to next Monday. On Thursday's class, I'll first solve this velocity profile thing analytically, and then you will solve this both analytically and numerically. I'll tell you what is the difference in numerical solution and analytical solution. Many of you already know. Those you know, they will come to know. Okay. Thank you for extra time. आज मैं थोड़ा ज़्यादा time ले लिया. Thanks.
Thank you, sir.
Thank you.
Excuse me, sir.
Thanks.
Thank you,
Don't
sir.
worry. You have another class, so you can take a break
Sir,
and
I
then you
just
can
want
join.
to say one thing.
Yes, please go ahead. Yes,
Sir,
Girish.
is this problem is analogous to the problem that we have solved in heat transfer of semi-infinite?
Exactly. Right. Heat transfer is unsteady state, right? Where like Fourier
Yes,
number and
semi-infinite.
Hissler chart, right?
Semi. Yes.
Yeah,
There the
similar to that.
function
Very
something
good.
sort of error function something. No, not exactly.
Exactly. No. So that's the correct answer. Error function. Yes. So that's the analytical solution. Very good, Girish. So the if you will solve analytically both problems, either this constant velocity flat plate or constant stress flat plate problem, both at early times. At early times, remember we are going to see the comparable time also when t will be equal to x square value. Here t is very less than x square value. Early times, the analytical solution is in terms of error function. That is in the slide also, and that's what we are going to discuss. Good, Girish. So don't worry about the submission of assignment. It's not due next Monday. Next to next Monday. Wait for the next class. But you can start thinking on those lines. I have given you the solution already, which we are going to discuss. Start thinking on those lines that how you will solve it numerically. It will be a good practice for you to how we code things, how we write the code on MATLAB or Python, whatever it is. So it's a good start. Thanks. Thank you, Girish.